All right, let's look at one more shadow problem. This only has two parts, so this should be a much easier problem. And just one more look at shadows. So a spotlight on the ground shines on a wall 14 feet away. A man 5.5 feet tall walks away from the wall toward the light at a speed of 3 feet per second. All right, so he's walking away from the wall and towards the light. The shadow is going to be over here because the light is on the ground. All right, so when it hits him, it's going to be over there. What's the length of his shadow? Again, we have similar triangles. So this length here, I'm not going to draw the triangles out because we just kind of looked at this. But this is the length we're, this is the length we're looking for, the length of his shadow. The spotlight shines on a wall 14 feet away. So this distance here is 14 feet. So there's two values, right? So one triangle is the distance from the light to the wall and the shadow, right? So x equals shadow. Actually, right over there. The other triangle is formed by the man, who's 5.5 feet tall. These are short men, I guess. And we don't have this distance. Let's see. A man 5 feet 5 point. Oh, exactly. Sorry, we do. When he's 12.5 feet from the building. So this distance here is 12.5 feet. If that distance there is 12.5 feet and the light and the building are 14 feet away, this is 1.5 feet. So I'm not drawing to scale. So we have one triangle that's formed by the 1.5 feet, the distance the man is from the light and the man. And then we have the second triangle that's formed by the distance between the light and the building and the shadow. Right? So here, when the man moves, like when the other problem, the man could just keep on moving because he's moving away from the light. Here, the man will be moving towards the light. There's not going to be a shadow problem once he passes that light. So let's find the length of the shadow. So this would be, we're looking for x. So x is to, I can't write over there apparently. X is to 5.5 as, we're comparing similar distances, height is to height, as 14 is to 1.5. It could reduce, not really, the 5, that's not really worth it. So let's just cross multiply. 1.5x equals 14 times 5.5. So that's going to be a very nice 77, but not so nice when we divide it by 1.5. 51.3333 feet is what the man's shadow is. How fast is the length of the shadow on the building changing? All right, so I put a little theorem here. We used it in the last problem, but I didn't really go over the theorem. This is straight from geometry, proportionality theorem. So the transversal divides parallel lines proportionally. Well, we did talk about that this distance here. So if the man is walking, he is walking away from the wall towards the light. So this distance is changing. Let me get a different color. Call it x. Oh, no, I've used x. Can't call it x. I should have called that one S for shadow, huh? All right, let's call it A, and let's call this B. All right, so as he moves towards the light, A is changing and B is changing. A and B are going to be changing proportionately to the transversals that are dividing the lines. So that would be the man and the shadow. Right? So A and B are divided proportionately. They are not constant values. Matter of fact, nothing here is constant other than the height of the man. That is constant. Everything else is changing. All right, so we want how fast is the length of the shadow on the building changing. All right, so again, we can compare our value, or let's write our rates of change. First of all, though, let's look at the rates of change that we know. Before we go writing any equations. So we have, so he's walking away from the wall towards the light. So that would be dA. Wait, no, sorry. He's walking away from the wall, so that's B. At 3 feet per second. Okay, so notice that in the last problem, the man could just keep on going. Here, if he moves 1 foot this way, right? If that he goes 1 foot that direction, he's got 1 less foot. So if I add a foot here, I have to subtract a foot here, right? Because I've only got 14 feet between them. So here, these are directly proportional because I'm limited to the 14 feet. If B here, if dB dt, so he's increasing his distance between himself and the wall because he's walking away from the wall. So dB dt is 3 feet per second. dA dt has to be negative 3 feet per second because there's only 14 feet there. And so as whatever rate he increases his distance from the wall, he's decreasing his distance to the light. All right? So hopefully that makes sense on this particular problem. It's a little different because of where the light is. It's not in, on the behind him. All right, so now we can set this up. So we're looking, we have a direct relationship between x and b, and 5.5, that the only thing that's not changing is the man, and a. All right, so those are directly proportional. Use the proportionality theorem. Let's cross multiply. So we have ax equals 5.5b. I do have a product here, so I'll have to use a product rule. So u is a. du would be dA dt. V is x, so dV would be dx dt. All right, so we've got the first, which is a, times the derivative of the second, which is dx dt, plus the second, which is x, times the derivative of the first, so x dA dt, equals dB dt. Excuse me, 5.5 dB dt. We need just a tad more space. If that picture was off to the side, we'd be fine. All right, so we're solving for dx dt. Let's move everything over. So we have a dx dt equals 5.5 dB dt minus x dA dt. And now let's just divide by a. So dx dt is 5.5, and we know dB dt. Let's just fill in the substitute at the same time because we're running out of space here. dB dt is 3 minus x, which we found, 51.333, times dA dt, which is negative 3. So it's going to just be a plus. And then divided by A, which is 1.5. All right, and so now let's solve that out, and we're done with this problem, and that's it for this video. That's a non-working calculator. All right, so we've got 5.5 times 3, and then plus 51.333 times 3. And all of that divided by 1.5 gives us 113.6666 feet per second. Man, that's changing fast. Yep. Well, it's already really big. So it's already 51 feet in the air. All right, so how fast is the length of the shadow changing? That would be dx dt, and that was 113.6666 feet per second. So pretty fast. All right, and that's it for me and Shadows. Thanks for watching. Bye for now.